Okay, so let's look at two applications of exponential and log derivatives. Not every, so each of these questions on page 12 and 13 have several parts. Not every part is going to be using a derivative rate of change, but overall it's a good question that involves some calculus. So here's the scenario. It's a warm summer day. I feel like I started telling a story. It is a warm summer day, and a glass of cold milk from the refrigerator has been left on the counter. Its temperature, Y, in degrees Fahrenheit, is after sitting on the counter for T minutes, is modeled by this function. So the Y is the temperature based on T time, which is minutes. And you can see 72 minus 30 times 0.98 to the T. So there's the recent a to the x type of number to the x power. Okay, so let's look at a few questions here. Again, not every single one will be calculus, but all of them are good questions. Determine the temperature of the refrigerator. Determine the temperature of the refrigerator. So here's what I want you to write down. There's just one thing we got to do here. I want you to write down what time we should look at. So take your pencil, write on your paper before we discuss. What time do you think this refers to? Say write it on your paper. Don't. I was looking at you. I was looking at everybody's kind of looking at me. But wait. Well, you might have heard. You might have heard the news. Yeah, I really like this question because I'm kind of like, wait. All you have is a function based on time. So we need to think about time. Well, the temperature of the refrigerator is pretty much right when you pull it out of the fridge and set it. I mean, it's assuming you just immediately set it on the counter. So that would be a time of 0, like it just came out of the fridge. So it should still have the temperature of the refrigerator. All right, so basically, the question is f of 0. So we're going to do just plug in 0. So you'd have 72 minus 30, and anything to the 0 power is 1. And so it's 72 minus 30, which is 42 degrees. I said explaining your reasoning on these. I'm kind of talking through it. I just said it there. So if you want to write down, just that's when you pull it out, set it on the counter. That's when it should have the temperature of the fridge right when you start. Okay, cool. Similar thing on B. So I want you to think about it, write your answer down first, then we'll discuss. In part B, determine the temperature of the room. Okay, so all we have is a function based on time. Temperature of the room. And again, there's nothing rate of change here yet. So all we have is a function based on time. Think about what time we need here. Think about it for a minute. Try to write something down, and then we'll discuss. Don't you write a number down? Take a guess. You're not sure. Okay, so let's discuss for a minute. So I want to ask Sean here. I see up here Sean has 1,000. Why'd you say 1,000?
It's like at some point it's going to reach room temperature and it won't get any warmer. So
safe call might be even like 10,000. See, does that make sense what he said? Just the longer you set it out, eventually it's going to just reach the room temperature. It's starting out cold, it's going to warm up, and it's going to reach whatever the room temperature is. So Sean said plug in 1,000. I think that's a good call. If you'd rather plug in, I mean, I don't think 100 would be enough. 10,000 minutes would certainly probably be good enough. I think 1,000 would probably be good. Just a large number. So that's the explanation I'm saying here. Some significantly large number. Now really, does anybody know what concept we're representing as we say a number that gets larger and larger? Concept. We're talking about the limit. We want the limit as t really goes to infinity. It's actually an infinite limit question. If we think about it in terms of calculus. So if we take our time and just have to go to infinity, then it's eventually going to reach the temperature of the room. So you can evaluate this, the limit of this function as t goes to infinity, or you can just plug in a significantly large number. So we'll stick with 1,000. I wonder what I did. Oh, I did the limit question actually, so that was fun. Anyways, we'll just do f of 1,000 and. So you guys could evaluate that for me. Again, I did the limit question. Thank you. Yeah, plug it into your calculator, see what you get here. Just plug it in there.
I have it. I got 70.
You did only one. But thank you. 71.9999995. I think it's really about 72 actually. Yeah, if you did 10,000 or a number bigger. So basically what it's doing is, because this number is less, like, remember decimals and raising them to a power, a number between 0 and 1, if you raise it to a large power, if you're getting 98% of this, then 98% of that number. 0.98. You're continually getting a smaller number here, and so this number actually eventually goes to 0. Well, sorry, this does 0 times 30. So it's taking the 0.98. That's eventually becoming 0, essentially. So the room temperature is about 72 degrees. Okay, those two kind of work together. One T 0, one is T infinity. Any thoughts on those two? Okay, let us move on. When when is the milk warming up the fastest? Okay, so when, asking for time, kind of what we've been doing. Warming up, so that is the key word there. So this is now changing, right? It's the temperature is changing, it's warming. And that represents a rate of change. I'm just going to put ROC. Warming up the fastest. I should even put IROC, instantaneous rate of change. So basically on this one we need the derivative. So the derivative of, so I'm doing the difference rule. There's a minus, so I can do each derivative separately. The derivative of 72 is 0. Okay, then I have negative 30 is the coefficient. Negative 30 times 0.98 to the t. Negative 30 is coefficient. Any coefficient we can bring down. And then I'll evaluate the derivative of 0.98 to the t. That is a to the x. And the derivative of a to the x is a to the x ln a. So it's going to be 0.98 to the t. ln of my base, 0.98. Oh, and then, by the way, we're first going to find the time, and then we'll find the actual rate. So I guess I'm kind of doing two more here. Yeah, I'm sorry. I'm actually already finding this. So. Anyways, that's the derivative. We will need that. So we good there? We just a to the x, that rule. I notice here I kind of need to answer two questions. I'm already doing this second one. So the first question I should really answer here. What time will the milk be warming up the fastest? So raise your hand if you'd like to answer that one. What time? 2 minutes, 20, 1,000? Just think about it conceptually. Andrew?
I was gonna go probably like after like a minute until.
5 minutes is pretty good. I think there's another time that it'll be warming up even faster though. Too close.
When it just comes out of the, like right after you take it out of the.
So roughly a time of
1 second.
0. Yeah. Basically right when it comes out. Wait, does that make sense? Because it's cold entering a warmer environment, so that's when it's going to be warming up the fastest.
Whoa.
After an hour, it's already a lot warmer, so it's not warming up as fast.
Since we use 0 for the refrigerator, shouldn't we use something like 0.01?
Well, no, we're still going to do 0, but we're finding, so that's when it's warming up the fastest. Now we're going to do the rate. So what is that rate? Like 2 degrees a minute. I think we're in terms of degrees per minute. So something like that. 2 degrees a minute. Maybe that's what's warming up at. So this one, though, the difference between like what was it, part A or something, is instead of f of 0, it's f prime of 0 to find the rate. Sure.
Yeah, I kind of have the same question because if time hasn't happened yet, if that hasn't started, then the milk's still in the refrigerator. So wouldn't it have to be like 0.1 or something?
No, we're assuming it's just they're instantaneously like the same. Like you pull it out and it's just right on the counter right away.
Okay.
So, sure, there's in all reality, yeah. I mean, there'd be at least probably 1 second that you take and put it on there. We're just starting the clock, assuming it's directly on the counter. So. Okay, so let's plug in 0 now. So that's the derivative. This will be the rate of change. We plug in 0. The rate of change at 0. So we got negative 30 times 1. 0.98 to the 0 is just 1. And then natural log 0.98. Somebody else put that in their calculator, please. Don't want Caroline to do it all.
Yeah.
It's be rounded as well.
To what place?
Hundreds, let's do. So Chris can tell us.
0.61
Thank you. 0.61. This was in degrees per time, which is minute. So, or yeah, if you did 0.6, they don't really say what's around to. So about 0.61 degrees per minute. Now, if you tried it at any other time, moving forward, time a second or 1.5 seconds or 3 minutes. Oh wait, I'm sorry, 1 minute. Half a minute, 5 minutes. The rate would be below this. It might be like 0.45 degrees a minute or something. So this is the fastest when it's warming up the fastest. Okay. So other questions could be asked about a rate of change at any other time, really. So it's warming up the fastest at a time of 0, and we found the actual rate there. Let's do the last 2 questions to finish up this one. Determine algebraically, so by hand, when the temperature of the milk reaches 55. So this is temperature, not rate of change. Okay, not the rate of change of the milk, of the temperature of the milk. Just temperature. That was F. Or, well, I called it Y. Yeah. Originally I had a Y, I changed it to F. So F or Y. So we need when F of T, our temperature, is 55. So I mean, this is. Does it kind of seem like the position and velocity and acceleration questions, where it's just like you have the numbers, but you guys just got to decide where to plug them in and stuff. So this is where our original function is 55. So I'm setting 55 equal to my original function, the 72 minus 30, 0.98 to the t. And I'm going to solve. It's been a while since I think maybe if we haven't done these this year, maybe you did them last year, but solving a log equation, or well, solving an exponential equation will involve some logs in a minute. So to solve these, here's a review of this. Isolate the exponential term. So I'm going to isolate this term. So I need to do combine these others. Do not do 72 minus 30. That's a common mistake. Those are not, like the 30 is times the 0.98 to the t, so order of operations says you cannot combine those. But I can subtract 72, get negative 17 equals negative 30 times 0.98 to the t. Then I can divide by negative 30. Negatives cancel. I'll write it over here. 17 over 30 equals 0.98 to the t. And I'm just going to leave it as a fraction. If you want to do a decimal, you could at this point, but leave it as a fraction. So I don't think we've done these this year. Solving for an exponential t. What do you do now? No. What? Yes, then you throw a log at both sides. And that will, I choose natural log, but you can choose whatever base you want. Throw a log at both sides, and that will bring the t down. And then we can work it out from there. So I'm just going to rewrite the left side, natural log of 17 over 30. So then the t comes down. This is the property of logs. Bring t down in front, ln of 0.98. And finally, solving for t, divide by natural log of 0.98. And then just put that in your calculator. Write my final answer over there. It is good practice too to make sure you're entering these correctly. Somebody else? Mary Beth, did you get it?
Yeah, 28.1.
Yeah, that's what I got too. And that's 28.1, and this was minutes. And I mean, it makes sense. I mean, just logically, like there's started at a temperature of 72 degrees at a time of 0. After 28 minutes, okay, sure, it's down to 55 degrees. By the way, these are all pretty realistic. I mean, I don't know if it's perfect, but roughly what a fridge would set the temperature at. What happens? Last one, any thoughts on A through D? Okay. So at what rate? So we're back, I'm going to write IROC. We're back to a rate of change. At what rate is the milk warming when its temperature is 55? This flows directly from part D. We just found in part D that at a time of about 28.11 minutes, at about 28.11 minutes, that's when the temperature is 55 degrees. And so at what rate is it warming then? At 28.11 minutes. Well, the rate of change was in part C. Let me write it down again. It was just the derivative. F prime of t was what? Negative 30.98 to the t ln 0.98. Alright, 2, we have a rate of change function based on time. And so, yeah, that's why we did part D, because now I have the time. And I can just put that in this function. And evaluate. Now, just make sure when you're entering it in, the best way to do it is to leave it in your calculator as 28.11, whatever the decimals are. At least 3 decimals is a good rule of thumb. Or what I would do is just put negative 30.98, and then you put the answer button on your calculator. Right, or either to your previous answer and then times that 1.98. So by the way, what you should get here, this is after 28 minutes, so it has to be less than part C. Right, that was the maximum rate, 0.61 degrees per minute. So it has to be definitely less than that. Get something, Kelly?
0.34.
Yeah, I got about 0.3. I wrote 3, but yeah, sure, you're good. 0.34 degrees Fahrenheit per minute. Okay, so really like this question. Part A and B were kind of conceptually thinking about the times. Part C, D, and E then actually involve a little calculus, rate of change function, and some logs in part D. A good question, kind of combines some of the things we've been doing. You notice a lot of these too, we do the derivative and it's pretty minimal. We only did it once, that was kind of the only major calculus part, but then we plugged other things in. Well, any thoughts on that one? Questions I can answer? Let's flip it over and do one more. This one is about the spread of an illness, the spread of a virus. And so this is going to be the spread of a flu in a school is modeled by this equation. So again, they give it to you. This one is an E, right? E to the T power down there. Where P is the number of students infected, and T is the days, number of days, after it first started. So it's at a school. P is the number of infected. T is the number of days after it started. So let's look at 4 questions. Here's the first one. Estimate the initial number. So initials at the start. The initial number of students infected. The number of students infected at the start. So here's our number of affected students, P. There's the function. Again, I'm going to ask, because we have a function based on time, what time is this? And yeah, I see a lot of you saying 0. Very nice. Initial is, yeah, whenever you see that word, it's kind of a clue. It's going to be 0. Okay, so just got to plug in 0 there. So I'm really in P of 0. So it'll be 200 over 1 plus, and then 5 minus 0 is 5, so it'll be e to the 5th. Now when you do this, this is e to the 5th, that's not going to really be a whole number. So you get a decimal, right? What did you get?
1.34.
Yeah, about 1.34. So that's it. But what's the initial number of students? Well, you can't have like 0.3 of a person. So more in the case in the context of the problem, 1 person if you round down, or 2 people if you round up. Which kind of makes sense, right? 1 or 2 people would have a virus. They come into contact with other people, then it will spread. I'm writing people, I guess it's students. So you round down 1, you round up 2. Sounds like that was time of 0. Next, let's do how fast, part B, how fast is the flu spreading after 4 days? How fast? So again, I kind of circle some key words here. 4 days is this is my time. Right. T was in days. How fast? This is a rate of change. Right, this is our instantaneous rate of change. So I need to do the derivative and then plug in 4. So let's do the derivative. So I'm going P prime of T. Now this one, 200 over the 1 plus e to the 5 minus t. Certainly a fraction, quotient, so I'm going to do quotient rule. So I'm going to do low, 1 plus e to the 5 minus t. D high is 0, derivative of 200, minus high, which is 200, and then d low. So the derivative of the low, the derivative of 1 is 0, and then I need the derivative of e to the 5 minus t. So here's just a review of derivative of exponential. The derivative is itself, e to the 5 minus t, times the chain rule, the derivative of the exponent. Derivative of 5 is 0, derivative of negative t is negative 1. So I'll put times negative 1. All over low squared. I'm just going to clean it up ever so slightly because there's not really anything really much to combine at all. So we could actually, if you want, you could plug in 4 right now. Okay, because that's what we're trying to find. I'm just going to clean it up just ever so slightly. This negative 1 times this negative 200 is positive 200. So I'm just going to write 200 e to the 5 minus t over this, the 1 plus e to the 5 minus t squared. And then we're going to plug in 4.
Why isn't it negative 200?
Because this negative 1, these are all multiplied, so I can put it anywhere. And really I just put it here and multiply those.
So it would be okay if we didn't put it in, but
If you left it as negative 200 and then e, and then left it like that and plugged in 4. If it just asked for the rate of change function, then you'd simplify it to this. So now I'm just doing p prime of 4. So 200, I'm plugging in 4, so this is going to be e, right? 5 minus 4, e to the 1. On bottom, similar, 1 plus e, because 5 minus 4 is the first power, and then squared. And then you'll need a calculator. This is going to be students. How fast is it spreading? The number of students per day. Pretty good.
39.3.
Yeah, I got about 39. So I said 39.3 or something. So it's it's spreading pretty quickly there. So let me stop there before I hit C and D, really to finish up. Any thoughts on A or B there? B might be the best calc question, seeing as do a quotient rule, chain rule, plugging in 4. That's a nice question. So I realized on part C, what we're going to need to do. When will the flu be spreading at its maximum rate? Here, let's actually discuss it first, and then definitely need a calculator in this one. I'm going to pull up mine. So I even say here. So when will the flu be spreading at its maximum rate? We're basically finding this is the rate, right? How fast? Here. So So we're trying to find when that is at a maximum. There's a calculus way to do this where we do the second derivative, okay, of this. I realize that's a little, we could do it. It's a little more than I'd like for us to do though. So instead I'm going to have us do, just using our graphic calculator. So max rate. So this is the rate of change function, p prime. I'll put p prime in T. That's the rate of change function. We want to see where on that function it's at a maximum. So basically, we're just going to graph p prime and then look for a max. So you can try it out on yours. I'm going to try and do it as well here. Yeah, there we go. Okay, so hopefully you're getting something like this. You might have to, on your graph calculator, you might have to hit zoom fit 0. Basically, you should be getting a parabola if you put it in correctly. And we can see that the maximum occurs right here. It's our x coordinate. Halfway from 10, so it's going to be at 5. The maximum students per day is right here, 50. And this graph makes sense, right? I mean, it's usually your body will fight off the illness, and so less students are getting infected per day, or maybe it infects everybody, so less students are getting infected per day as well, and so it naturally will decrease. So anyways, 5 days. So when, yes, 5 days. If it had asked, what is the maximum rate, it would have been 50. Right? Is that, whatever it was here. Yeah, 50 students per day. We'll learn next unit especially. There's another using the second derivative we could have found that answer. Well, last one here with D. Let's do that and then I'll see if there's questions. Determine the maximum rate the flu will be spreading. Kind of already answered there, but now that we have this, we can actually do it by hand. So I should have said algebraically, let's find this. We know it's 50. We saw from the graph. At 5 days, it's spreading 50. Let's just see that algebraically. We would just plug in 5 into our derivative. So I'm going back up to my derivative. 200e to the 5 minus t. Well, that'll be 200e to the 5 minus 5, which is 0. And the same thing happens on bottom. 1 plus e to the 5 minus 5, which is 0. E to the 0 is 1, so it's 1 times 200. E to the 0 is 1, so it's 1 plus 1, which is 2. And that's squared. That'll be 4, and 200 divided by 4 is 50. Putting students per day. Okay, so you can see algebraically by hand how we got that. Well, let me open it up to questions on the second one there. parts.